Okay, today I'd like to talk to you about something called the mole. And this is a concept that strikes fear into the hearts of many a chemistry student, but it doesn't have to be that way. See, we've been talking a lot about relative mass and relative masses of atoms, and we learned that the masses that are listed on the periodic table are just relative masses. 63.546. That's the atomic mass of copper. We learned that that's just a relative mass, that copper is, all that means is that copper is approximately 5 times the mass of carbon. Okay? So they're just relative masses. And I mentioned that the reason this is important is because we're going to use this when we start to do math with chemical equations. Okay? When we start to look at mass relationships, in chemical reactions, that's really what we're looking at in the future in this we won't really get to it until next semester, but that's where we're headed, and that's what we're really interested in. And so we need to be able to work with masses, and chemical reactions happen though in terms of atoms. So you might take a reaction like this, and all of these numbers here, the coefficients and the subscripts, refer to numbers of molecules and atoms, not to masses. So these numbers refer to molecules and atoms, not grams. And so we've got a problem then. Chemical reactions happen according to atomic and molecular ratios, not mass ratios. So think about John Dalton's, one of his postulates, that compounds form in small whole number ratios of atoms. And that's how chemical reactions happen too. They happen on the basis of atoms and molecules. They don't care about masses. And yet we can't count atoms and molecules in the lab. We have to use masses. Now, of course, what we're going to do is we're going to use the system of relative masses to do those sorts of calculations. But how can we do that? How can we use these masses? How can we use these masses? They don't really have any units. The so-called atomic mass unit, AMU, is not really a unit. It's just a name to throw on these relative masses. Okay? So how can we use these? Can we somehow turn them into grams? Can we convert atomic mass units into grams? Well, we could, but see, the important thing here to remember, the important thing is the ratios of atoms and molecules. The important thing is actually the ratios of atoms and molecules. What I mean by that is this equation, the important thing in this chemical equation is that it is a 2-to-1 ratio of hydrogen to oxygen molecules required. All right? Or a 2-to-2 ratio, a 1-to-1 ratio of hydrogen required to water produced, and so on. So it's really the ratios that are important. So now we need to realize this, that if we take any of the atomic masses, let's say 12.01 grams of carbon and 63.546 grams of copper, or 1.01, I'm sorry, not grams, these are AMU originally, right? If we take all these average atomic masses of these elements, these are all originally for one atom. So for example, what we're saying here is one atom of carbon is 12.01 AMUs. One atom of copper is 63.546 AMU, and one atom of hydrogen is 1.01 AMU, okay, atomic mass unit. And again, those are just relative masses. They're all compared to carbon 12 being exactly 12. But what we can do is a little trick. if I just slap a G on the end of these for grams, so in other words, now I'm talking about 12.01 grams of carbon, 63.546 grams of copper, and 1.01 grams of hydrogen, I no longer have a single atom, okay? That's clear, because I've just made these masses very large. All right, a carbon atom does not weigh 12 grams, and a single copper atom does not weigh 63.546 grams. But what I have done is I've created masses of each of these three elements that contain the same numbers of atoms, okay? So all three of these samples, you might say, let's say these are three samples, a 12 gram sample of carbon, a 63.5 gram sample of copper, and a 1 gram sample of hydrogen. All three contain or have the same number of atoms. All three of those have the same number of atoms. Now let me prove that to you. Okay, I'm going to make a little table. And in this table, I'm going to put carbon and nickel. There's no particular reason I picked these elements. And now I'm going to write here the masses. Okay, so one atom of carbon is 12.01 atomic mass units, and one atom of nickel is 58.69. That's right from the periodic table. Okay. And then what I want to do, though, is the mass ratio. So in other words, if I take 12.01 and divide it by 58.69, I get 0.2046. All right, that's the mass ratio of carbon to nickel. Now, what if I take two atoms? Well, for two atoms, I would have 2 times 12.01 AMU, and 2 times 58.69 AMU. And my ratio then of carbon divided by nickel would still be the same. Because, of course, the 2's cancel. Right? Now the same thing would happen if I did 10 atoms, for example. If I have 10 atoms, then it's going to be 10 times 12.01 and 10 times 58.69, and the ratio will still be the same. Or if I had 1,000 atoms, right? 1,000 times 12.01 and 1,000 times 58.69. The ratio is still the same. Now watch this. What if I have 12.01 grams of carbon and 58.69 grams of nickel? What's that ratio? 0.2046. All right? The numbers of atoms must be the same in these two samples because the ratio is the same. As long as the atoms are consistent in their mass, have a consistent average mass, then if this ratio comes out the same, the ratio between these two samples, then the numbers of atoms must be the same in those two samples. Okay? So this concept then can be useful because by weighing atoms then, by weighing the different elements, we can look at their mass ratio and turn it into an atom ratio, or vice versa. We could take an atom ratio in a chemical reaction and turn it into a mass ratio that we need to use. All right? We could take an atom ratio in a chemical reaction and turn it into a mass ratio. All right? For example, let's say I had copper, and copper was going to react with iron, and we did this little experiment in our lab, right? And it's going to react like this, and it's going to produce solid copper and iron 2 plus ions dissolved in the solution. All right? Well, what this equation means is really 1 atom of copper plus 1 atom of this produces 1 atom of this and 1 atom of this. All right? Well, what about masses? Let's say I want to make a certain mass of copper. Maybe I want to make 63.546 grams of copper. All right? That's actually the atomic mass of copper with a little g slapped on the end of it. Well, how much iron would I need to make that? I would need 55.847, and that's the atomic mass of iron. All right, see how that works? And how much copper 2 plus would I need? Well, I need 63.546 grams of that. Of course, I'm not going to add it just as the ion, but as part of copper sulfate. But that's okay because I can take copper sulfate, which is CuSO4 and 5H2O, and I can figure out what the mass of that is going to be. I can figure out what mass of this I would need. All I have to do is take, well, 63.546 grams of this is the same number of atoms as 32. Let me get this here, 32.066 grams of sulfur, and now I have 4 oxygens, so that's going to have to be 4 times 16.00 grams for the oxygen. And then I have 5 waters, and water is 2 hydrogens and an oxygen. It comes out to about 18.02 grams, and that's going to have to be times 5. All right. Now let's see what I get here. I'll wait for my calculator to come up quickly. Okay. Now, so 63.546 plus 32.066 plus 4 times 16 plus 5 times 18.02 gives me 249.712. All right? So I need 249.7 grams of copper sulfate pentahydrate to react with 55.847 grams of iron, maybe in the form of steel wool, to produce 63.546 grams of copper. Now this sort of calculation is beyond what we're going to do right now. This is going to come next semester when we're actually doing what we call stoichiometry. We're looking at mass relations in compounds and in chemical reactions. For now, I just want you to realize this, what these values are right here. In other words, the atomic mass with a G on the end, also called the gram atomic mass. That's the gram atomic mass of iron, and 63.546 grams of copper is the gram atomic mass of copper. And 12.011 grams of carbon is the gram atomic mass of carbon, all right, and so on. Now, all of these masses, they can be called the gram atomic mass, all right, but they also have another special name. They're also called 1 mole of each of these elements. All right, and the word 1 mole is really just short for 1 molecular weight. All right, an older term. It's really not a weight, of course, it's a mass, but you still see that around in chemistry. So 1 mole is 1 molecular weight. All right. Now, so what is 1 mole? You can easily get 1 mole of any element. Just look at the periodic table. Okay. Now, I made a special periodic table of moles here that we can look at. And all I did on this table is I took a normal periodic table and I just put a G on the end of each of the atomic masses. And this becomes then a periodic table of moles. Okay, if you want to know how much a mole of carbon weighs, it's 12.01 grams. Now here's the thing. 12.01 grams of carbon contains the same number of atoms as 14.01 grams of nitrogen, or 16 grams of oxygen, or 19 grams of fluorine, or 40.08 grams of calcium, or 44.96 grams of scandium, or 88.91 grams of yttrium, or 178.5 grams of hafnium, or 195.1 grams of platinum, 197.0 grams of gold, 200.6 grams of mercury. All of those masses of those elements contain the same number of atoms. All right? And it turns out that that number is about 6.02 times 10 to the 23rd, which is a number called Avogadro's number. So, as it says down here, a mole of any element is the gram atomic mass of that element. The gram atomic mass of any element contains the same number of atoms, which happens to be 6.02 times 10 to the 23rd, also known as Avogadro's number. All right, so we can do calculations with this. We can ask things like this: what is the mass of 1 mole of carbon? All right, and then the answer, of course, is 12.011 grams. But we can go and get a little bit more complicated. We can say, all right, well, what is the mass of 1.5 moles of carbon? Or let's stop short of that first. Let's say 2, because it'll be easy. 2.0 moles of carbon. Well, obviously it'd just be 2 times 12.011 grams, right? Or 24.022. What if we make it a little bit more complicated, and let's start to use the factor label method here, which is what we should be using. What's the mass of 0.27 moles of carbon? Well, here's how you do it. You start with the quantity given, 0.27 moles carbon. And let's remember why we're doing this. We wouldn't be doing this in a vacuum like this. You wouldn't really be just asking just this question. What you'd be doing is you'd be working with a chemical reaction or a chemical compound, and you'd be trying to figure out how much of it you need. All right, what mass of it you need to make a compound or to complete a reaction. So in this case, though, and we're using the factor label method here, so we're going to put mole in the denominator, and we want the mass, so we're going to put grams up here. So what does that say? Grams per mole. Well, what is the grams per mole for carbon? Because we're talking about carbon here. It's 12.01 grams in 1 mole. So my equation here becomes 0.27 times 12.01, which gives me 3.24 with 2 sig figs will be 3.2. So if I need, for a chemical reaction, 0.27 moles of carbon, then I'm going to get 3.2 grams, weigh it out on the balance. See how that works? And we can ask, we can go backwards here. How many grams, or how many moles are in, let's say 1.00 grams of copper. So let's say I have a gram of copper. How many moles is that? Works just like this. All we have to do, follow our method here. Put grams of copper down here so that we can cancel it out. In the top we want moles. And 1 mole is 63.546, right? Just consult your periodic table of moles. Or your regular periodic table, just slap a G on the end of that atomic mass, and you have a mole. And that's all you have to do. And now we've got 1 divided by 63.546. Okay, and that gives us 0.0157. All right, with 3 sig figs. 0.0157 moles. Okay, and that's about 1% of a mole, which almost 2% of a mole. So I guess that makes sense. All right, make sure we did that right. 63.546. See how that works? Very simple. And let's say that well, actually, let's not say that. Let's save that till next time. We're going to talk a little bit more about this number next time. All right, and we'll do some problems in class.